I remember the last words my Nana told me before she died. She looked at me and she said, "Why are you coming at me with that hammer?" Ooh, that is a really dark joke. I'm sorry guys, that's inappropriate. Don't even repeat that joke. That's inappropriate. Alright guys, we are talking about entropy this lesson, and that is disorder, entropy. So this is the third lesson in thermodynamics. Let's get rolling. Let's talk about disorder. So entropy is represented with a capital S, and it is the measure of disorder or randomness of particles that make up a system. That's what entropy is. It is the measure of disorder. And it's based off of the law of disorder, that spontaneous processes always proceed in such a way that the entropy of the universe increases. The universe is getting more and more disordered. And let me put this in terms that hopefully you could relate to. If you were to make a sandcastle, the sand grains would be in a very ordered structure to make your really cool, or not so cool, to make your sandcastle. You'd be organizing the sand. If you were to come back a week later to the beach, I think everybody would expect that their castle would not be there anymore, because the wind, people, birds, waves, whatever it is, we know that it's probably going to move these sand grains around, and it will probably be in a very disordered way. They'll be mixed all around the beach. Things become more disordered. Even though the sand is moving around the beach, they aren't going to randomly become a sandcastle. They're not going to, I mean, they could. I mean, it's random. It's astronomically unlikely, but things are just moving in a random, more disorganized way. So if things keep going more random, it becomes more and more disorganized. That's the law of disorder. Entropy changes associated with changes in state can be predicted. So I'm talking about state. When I say state, states of matter. So if we take a look here at different states of matter, I've got an example of of solid, liquid, and gas. And as we can see here, a solid, and as you should know at this point, solids, the structure is very structured. The structure is not changing. If you carve something as solid, you can expect to come back tomorrow and that line will still be there. So it's very organized. Where in a liquid, it's not nearly as organized as a solid, but still, if you came back tomorrow and looked at this beaker, you would still expect there to be water in this beaker. This water molecules wouldn't leave, more or less. So, but if you were to try to make a mark in the water, that certainly is going to change. So there's more disorder in a liquid than there is in a solid, and a gas has even more disorder. The particles in this beaker are free to move out and fly out of the beaker and fly out of the room. So there's a lot more disorder in gas. So as we move from solid to liquid to gas, we are increasing the entropy. Entropy is increasing as we move from solid, liquid to gas. So that's about phase changes. Okay. So if we're going from a liquid to a gas, the entropy is increasing. Gases have much more randomness, much more disorder than a liquid. So therefore, the symbol, the change in entropy for the system, it would be this reaction here, this process, is greater than 0. In other words, it's positive. So this is increasing in entropy. Here is methanol solid turning into methanol liquid. Again, we have solid becoming a liquid. The solid is much more organized than the liquid. The liquid is much more disorganized. So if it's increasing in disorder, you're increasing in entropy. And I often like people to give advice that just substitute the word entropy for the word disorder. So as we go from liquid to gas here, we are becoming more disordered, so that means there's more entropy. As we move from methanol solid to methanol liquid, we are becoming more disordered, so therefore it's greater, more positive entropy. So when you dissolve a gas in a solvent, this always results in an increase in entropy. So think about this. When you have a gas, the particles are free to move around, but when you dissolve them into a solution, into a solvent to make a solution, there's always a decrease in entropy. So like carbon dioxide gas has a lot more disorder than carbon dioxide dissolved in water. And there are gases dissolved in water. That's aqueous. That's how fish breathe. There's dissolved oxygen in water. So as you go from a gas to aqueous, you're getting less disordered. So therefore, the change in entropy is less than 0 or negative. The reverse would be true, or the opposite would be the opposite sign here too. So aqueous carbon dioxide becoming gaseous carbon dioxide, like when you open up a soda, you can see that aqueous carbon dioxide coming into a gas and being released. That is more disorder, so that would be positive entropy. So if I go the reverse of this reaction, I would reverse this sign as well. Wow. So assuming no change in physical state, the entropy of a system usually increases when the number of gaseous product particles is greater than the number of gaseous reactant particles. So if I have a gas of sulfur trioxide, I got 2 moles of sulfur trioxide becoming 2 moles of sulfur dioxide and 1 mole of oxygen. This is a balanced equation. In this here, I would say that there is an increase in entropy. So the entropy of this system is greater than 0. It's an increase in entropy. Why is that? Well, think about this. I have 2 moles of product becoming 3 moles of gas. 2 moles of gas becoming 3 moles of gas. What's really important is this state. If you create more gas particles, you're creating more entropy, more disorder. So this example here, we have more entropy because we had 2 moles of gas becoming 3 moles of gas. Doesn't matter what the gas is, okay? These states of matter are very important. And let's even go back to this last one here. Or not last one, this one way over here. These states of matter are what's important. Does it matter that it's methanol? No. It's a solid becoming a liquid. Does it matter that it's water? No. It's a liquid becoming a gas. So it's the state of matter that's really important here. Okay? With some exceptions, you can predict the change in entropy when a solid or liquid dissolves in a solution. So let's think about this. Salt, table salt, sodium chloride, it's a solid. When we put it in water, mix it up, we'll find that it disappears, it dissolves. It's not gone, but what it is, it's turned into an aqueous solution of sodium ions and chloride ions, and you don't see it anymore. It's now in solution. When things are aqueous, that means they're dissolved in water, and you can't really, it's a homogeneous mixture. It's dissolved as part, you don't see it. It's surrounded by water molecules. But anyways, what would be more disordered? Sodium crystals, sodium chloride crystals, or sodium and chloride ions floating around in water? Hopefully you can understand at this point that sodium chloride ions are much more disordered than a crystal of sodium chloride. And this would go true also with solids. That's an example solid, but it would also be true with liquids. If I put a liquid into an aqueous solution, so let's say I had liquid ethanol and I poured liquid ethanol into liquid water, I would create a solution and you would have aqueous ethanol in there. Think about it like you have a pure substance and then you're mixing things up. It becomes much more disordered when you do that. So taking a liquid into aqueous, now it's mixed with water, that's more disordered. An increase in temperature of a substance is always accompanied by an increase in random motion of particles. Remember, temperature or heat is the kinetic energy of particles moving. So if you increase the temperature, you're increasing that kinetic energy. So if you increase the kinetic energy, you're creating more movement, more random motion. That would mean that you're increasing entropy. So whenever you add heat to a system, the entropy of the system will change in a positive way. You're going to create more disorder if you increase the temperature. Okay. What I want you to do here is read these and answer these questions. Pause the video and then I will give you the answers and explain. But remember, when you pause the video here, make sure that you not just tell me the signs, but explain why. And this is all just kind of review on the lesson I just gave you. So pause. And now we're back. Let's take a look at how you do it. So the first example is a negative change in entropy. Why? Because you have 2 moles of gas becoming 1 mole of gas. See, I've got 2 moles of gas here becoming 1 mole of gas. This is less disordered when 2 moles of gas become 1 mole of gas. In the second one, I'm saying that the entropy is negative also. Well, the reason for this one is because I have gas becoming aqueous. I'm putting a gaseous substance which has a lot of disorder into an aqueous solution, so I am decreasing the disorder. So it's becoming, it's a negative change in entropy. For C, I have methanol liquid becoming methanol aqueous. I'm taking liquid methanol, which is a pure substance, and I'm pouring it into water. That's what aqueous means. It's in water. So I'm pouring this pure methanol into water, and now it's dissolving in water. And this would be an increase in entropy, because before I had a very organized single situation here of just it's a pure substance. And in this situation here, it's no longer a pure substance. So I am increasing the entropy when the liquid becomes aqueous. It's mixed up with water, if that makes sense. And then the final one, we have C10H8 liquid becoming C10H8 solid. This is a negative change in entropy because a liquid is becoming a solid. It's becoming more ordered. The reason for this one is a state change from liquid to solid is a more ordered situation. So hopefully you understand this stuff. Entropy and questions that I'll ask you is really just looking at things and seeing if you can figure out the signs. So please review your notes, pause the video at this point again, and see if you can remember the correct answers in the future. And I will talk to you soon. Thank you.